Welcome to this video lesson. Today we will be looking at analyzing one-dimensional motion using position. Welcome to the second topic, and now we have moved to the realm of motion and its application, and we're going to be focusing on kinematics, which is the motion without talking much about the forces themselves that are causing the motion, but what is motion and how can we measure it and what are some of its applications? So the central idea here is that motion can be described and analyzed by use of graphs and equations. I'm going to move on to the very first section, which is analyzing one-dimensional motion using position. Learning goals for this section would be to discuss measurement techniques for motion, using dot diagrams to describe motion, using dot diagrams to sketch position time graphs, and one-dimensional vectors, position and displacement. So measuring motion, so you can think about what are some of the ways that you can measure motion, and there are many of them. So think about it first, and then you can pause the video and come back to it. When we're thinking about measuring the motion, there's many different ways. So we can have tools that would kind of be placed at a particular position, let's say right here. These are called motion sensor. And you can start walking away or towards it. And what this motion sensor will do is it will give you a position. So it will tell you, okay, right now you're this far away. If you move a little bit further away, you're this far away. And the way it does this, it will send a signal back and forth. It knows the speed of the signal and it takes the time that it gets back, and then it can use that and find the position based on the speed and time information. And it will keep doing this continuously, and as you walk, it will collect all of those data. The problem with a motion sensor is that when you get really far away, the signals that are coming, they're going to get disturbed by other objects, and that could be a problem. There are other ways of measuring motion. You can use what's called a ticker timer. With a ticker timer, the object carries this little tape, and this tape is attached to this device over here. Let's call this the ticker timer. And this ticker timer, well, what it does is it keeps punching a hole into this tape in equal time intervals. Let's say every 1 second. Each one is different. Some is 0.1 seconds, some are 0.06 seconds, and they're all different timing. So as this person is walking by, this is getting punched, and after a while you get this nice diagram where the dots are spaced differently throughout. So we can see because these are all in the same time interval, let's say every 1 second, that means there's little movement in 1 second, more movement in 1 second, even more movement in 1 second. So we know that in this case they're speeding up, and in this case they're kind of moving at a constant rate because they're displacing the same amount each time. There are many different methods and additional methods that we can use to measure motion as well, but the focus of today's lesson will just focus on these two ideas for now. We can also use cameras and other things, and they all have their own advantages and disadvantages. So one method that is used in physics to measure motion is using dot diagrams, and they're produced with this idea of ticker timer, where the ticker timer keeps punching holes on the paper every equal time interval. So it could be 1 second, it could be 0.5 seconds, it all depends. In these diagrams, the motion is traced in fixed intervals of time. So let's describe the motion for the following dot diagrams. So we want to do it in terms of slow, fast, slowing, I should say speeding up or slowing down. And whether it's constant and what is the direction. Let's look at our first one over here. I'm going to change my color to blue and I'm going to leave this descriptions here so we have an idea. So first of all, let's take care of the direction actually. Just by looking at the tape, we don't know what the direction is. So the object could have been moving in this direction, so the tape could have been being pulled in this direction or this direction. We actually can't tell based on this motion diagram. So I'm going to label. I'm going to assume that the person starts here and then ends here. And if that's the case, just by looking at the intervals of these dots, so let's say each one was taken every 1 second, the object moved this much every 1 second. Now comparing it to the next ones, we can see that this one has displaced much more and there's like really large displacements there. So in the very first one, because they're moving such in very small distances every single time or every single 1 second, I'm going to say this is slow. Is it speeding up or slowing down? Well, the spacing between them isn't changing, and since it's not changing, it's a constant pace. Constant or not changing. So another way of saying that is that the speed isn't changing. And in this particular case, direction, since we're assuming it starts from here and it goes here, the direction is east. And I will take, in order to say what direction it is, I'm going to assume a positive convention in the east direction. And in this way, it's moving in the positive east direction. If this was 1 and this was 2, it would be the opposite. It would be going in the west direction. On the second example here, we're going to make the same assumption starting here or here. And in this case, the object is moving a little bit faster because now we can see that the spacing in every second has increased. So this person initial punch was, let's say, here, and the next punch was here. So there's a larger distance traveled in every time interval. So let's take 5 seconds, for example. This one has traveled from here, 1 second, 2 seconds, 3, 4, 5 seconds. It's this much, and this one, 1, 2, 3, 4, 5 seconds is a much larger distance. So I'm going to say this is moving medium pace, or we can just say fast in this case. And taking this side to be positive again, we know that it's moving east from 1 to 2. And also, is it constant? Well, it's not changing. The speed, the distances here are all the same. So in this case, we have a constant speed. Now in the next one, you can actually try this one out on your own, and then we can kind of cover it. And if you think about this, you can see that initially every 1 second it's small, and then the next second it gets a little bit more distance, and then more distance, more, and more. So in this case, assuming that 1 is here and 2 is here, we know that the object is, so from 1 to 2, we know that the object is speeding up. It's from slow to fast, so I'm not even going to write it, and in this case it would be going in the east direction. We can also make an assumption that the object is going from 1 to 2 this way. So I'm going to say for purple 1 to 2. This object, initially if it was here, it was in the first second it traveled a lot, second less, third second less, fourth less, and less as time progressed. So in this case, the object was slowing down, and in terms of direction, the object was moving in the west direction. Moving on to the next one, you can try this on your own, and then we will talk about it. Okay, I'm going to make an assumption in this one that the object starts here and moves in the east direction here. So that's east. And in this case, you can see just by looking at it, initially it's getting faster and faster. After this position, it goes for a regular constant speed around this region, and then it starts to slow down. So how do we write this? Well, I'm going to break this down into what we call intervals. So in this case, because the speed is changing differently in different regions, it's nice to create what we called intervals to be more specific in certain regions. So we know that in the first region, it's speeding up to here, so up to 2, so 1 to 2, the object is speeding up and it's moving to the east. And then we can say that from 2 to 3, this region from here to here, this interval, they are going at a constant speed. They're going quite fast or medium speed, so medium slash fast speed, and they're moving in the east direction. And from 3 to 4, things are changing. In 3 to 4, large distance, smaller, 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 and smaller. So it's a little bit confusing here. My dots should have been spaced a little bit better, but in this case, you can see that large distance, and then it's getting smaller. So kind of it speeds up and then slows down, but let's just assume that the spacing here is a little bit more consistent. And in this case, it would be that from 3 to 4, the object is slowing down and it's still moving in the east direction. So the direction doesn't change. The object is still going this way, but you can see that the first second, a lot of distance is covered, less distance is covered, less distance covered, and less distance is covered. So that means the object was slowing down. So these are called intervals. And we have something else which is called events. So we can say this is the start of the event, like the very beginning event is the very beginning. And then the next event happens when the object has already sped up. And now they're from this event, from second to the third event, during this interval, they're going at a constant speed. And then they kind of stop going at a constant speed at event 3, and then between event 3 and 4, they're slowing down. So two new terms. One is interval, and interval refers to a time period that we can choose um, based on the situation. And in this case, we've chosen these intervals because it is able to help us be more specific about the motion in these regions. And the second terminology is events, and events are things that happen in a specific time and location. So in this case, the time was the very beginning and location was also the very beginning. This location is and time is when the object stopped speeding up and started moving at a constant speed, and event 3 is when the object stopped going at a constant speed and then started to slow down. So this is one moment in time when you're choosing an event, and intervals are usually time period between those events. Okay, dot diagrams and position time graphs. Let's get graphing. The position time graph is one of the most fundamental graphs that we will need as a physicist. For the following dot diagrams, 3 reference points, A, B, and C, are chosen. We are going to take the east direction to be positive, so that's shown here, so that's going to be our sign convention. We are going to draw the position time graph for the dot diagrams, starting from the reference point, going east in the top set of graphs, and going west in the diagrams below. So here's what we're going to do. So in this graph and this graph, the reference point is A. In these two graphs, reference point is B. And in these two graphs, the reference point is C. In the very first question, we're going to assume that we're moving from here to here. So those are the top graphs here. And for the bottom graphs, we're going to assume that we're moving from C to A. Let's first talk about how we draw, or how do we convert the graphs. So what I'm going to do is I am going to take a photo of this section, and I'm going to bring it up to here. And then I am going to take another photo of this. I'm going to take that to here, and I'm going to zoom into here. I'm going to zoom into here. Let's move this down, and it doesn't actually matter which one we're going to choose. Let us focus on B as our reference point, and that's the only one we're going to do. I'm going to pull it down all the way here, and if B was the reference point, that means that my reference and everything that I measure things from is going to be this point over here. So I'm going to draw a line over here. And my reference point on a position time graph is this axis over here. So that's going to be that first reference point. I'm going to start at point A, meaning that my first position is here. Then I'm going to be moving to the right. So in the first, I said in the top set of graphs, we're moving from A to C. So that's the first point. This is the second point, third point. So actually, I'm going to draw that down here in my position. So you can see in the positions, I'm taking right to be the east and positive direction. So if I'm going left, you can see the very first one at time 0, at the very beginning, that I'm going very far away in this direction. Then in the second one, a little bit less, and then less. And then this is going to continue. We're going to have, that's the third point, and then the fourth point, and then the fifth point. And then it keeps happening, and I'm going to have all of these kind of pointed, and then at some point, I am going to, it's kind of like a straight line, their spacing is the same, and I'm going to reach this B point right at the center. This is the B point. And after that point, I am going to start moving in the opposite direction. So I'm going to go in this direction, and that's positive for me. I'm saying that east is positive. So instead of drawing all my values in the negative side, I'm going to start putting them positive. The first arrow is small. The next arrow is going to be bigger. The next arrow is going to even be bigger, and so on. So these are moving higher and higher as we go. So to draw this, I'm going to continue this line, and you can see that that's kind of like my drawing. So if I were to take the reference at point B, I would get a nice straight line going up like that. So I'm going to draw this, and I didn't draw these very well, so that will go up there. So basically what we do when we want to draw this, let's do one at point C as well. So I will move this here, and I'm just going to quickly erase everything that I've done here, and maybe let's do an easier one. Let's do A. So I'm going to actually take this, and now I have a difficult time moving it. So let's do C. That's okay. For point C, it starts here. That's my reference point. So from C, my starting point, which is A, is extremely far away, and it's negative. So you can see that at the very beginning, I am like super far down. I'm more far down than I was last time. Last time I was only halfway down, and I drew it this long. So in this case, based on my graphing techniques, I would have to go all the way down here. And then I keep getting closer and closer to my reference point, and at the very end of my travel, you can see that this person moves, they get closer and closer to this reference point C, they pass point B, and then they keep going, getting closer and closer and closer and closer, and at some point, at the very end, you reach the reference point. From that reference point, your position was never positive, so you're never in this region. You're always in the negative region, but at the very end, you're zero distance away from the reference point. So at the very end, you are going to be right here. So a few things about this. You can see that the slope of the line from here to here hasn't really changed. The only thing that has changed is the position. So I will move everything to the right again. And you can see that for the first one, if I were to start from A, the slope wouldn't change. I will just go much higher. So let's do the graphs here. I'm going to start here. We know that for the, I'm going to zoom in. We know that, sorry, the program is being a little bit buggy here. We know that we are moving east in this direction, and we're moving next, and we're moving west, and this side is positive. So starting from A, for this diagram, you can see that we're moving very slow. I'm going to draw it starting here. That's my reference point. And from here, at point 0, we're right at the reference point, and then we're in the positive direction, a little bit more, a little bit more, a little bit more, and so on. So I'm going to draw this in a very, this time I'll draw it in a very much smaller slope than last time. For this question, you can see that at point B, B is the reference, so we're kind of measuring everything from here. So at the very beginning, we were to the left, so we're kind of starting here. We travel right about the middle, we reach point B, and then we keep moving, and you can see that after this point, which is right here, our position will become positive, positive, positive. So everything to the right of this reference point is positive, and everything to the left is negative. If we measured everything from reference point C, you can see that the starting point is very negative, and as time passes, you get closer and closer and closer to point C, but you're always in the negative region because everything measured from here, everything to the right is positive and everything to the left is negative. So that's going to look something like this. What happens if we were moving to the west? So let's see, for the very first one, we can see that we're here. Sorry, reference point is A. Initially, we're located right here. So I'm actually going to erase this one. And let's do purple. Initially, we are here. Our reference point is here. So initially, we are to the right of our reference point. So in our reference point, everything to the right is positive, everything to the left is negative. Initially, we're very, very far away from very, very far away from our reference point. And as we move towards A, we're getting closer and closer to the reference point. So the distance from here to here starting to decrease, 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 decrease. And when we reach point A, we are right at the reference point. Everything to the right, positive, everything to the left, negative, and right at that point is 0. So when we reach the end, we reach the point 0. And I'm going to draw a straight line through there. What if our reference is B? Well, no problem. Here's our reference. Everything on this side is positive. Everything on this side is negative. Initially, we're saying we're moving west, so we're starting here. From here to here is a positive distance, so we kind of go up. And then the distance starts to decrease as we go, so the distance is going to get closer and closer to the reference point. And then our distance is going to be negative. It's going to get bigger and bigger in the negative region until we reach there. So you can see that initially it starts positive, and then at some point it reaches 0. This is where the reference point is. And then we just keep going down to the negative side after. So it looks a little bit like this. You can see that the slope of these lines are all consistent, and slope of these lines are also going to be consistent. For the very last one, our starting position is C. So I'm just going to use a blue color to indicate that. So that's a reference. Everything this way is positive now. Everything this way is negative. So I'm moving to the west starting here. So I'm going to move. So at point 0, I'm at a 0 point. So I will label that here. And then I will move a little bit to the left, which is negative, little negative, larger negative, larger negative, larger negative. And as I go in this direction, I just get further and further away from my reference point in the negative direction. So I get further and further and further away from my reference point in the negative direction until I reach the very last point. And this is kind of how we draw things, and this is a constant velocity. So what we can notice from this, we can see that the dots are all spaced out, and what we notice from the graph is that when they're consistent speed, the slope of the line is consistent, it doesn't change, and we can see that the line is straight. Now, what happens if the spacing between the dots changes? Well, that means in the last one, actually, let's take a look. In the last one, we had a large number of dots. We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 dots. So that means approximately, let's say each dot was every second. So that's 20 seconds of time. Whereas in this one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 dots, but they're all spaced more. So in terms of time, last time we went all the way up to here. This time we're only moving half the time. It's only 10 seconds. But each distance is much further away. So we're going to start moving much further each time to reach here. So we'll end up from point A, if that was the reference, first point is 0, then we move a little bit, then we move more, then we move more, and so on. So if I were to draw this, I will get something like this. And I'm not moving as far this time. Taking B to be the reference, well, from point B, my first point when I'm moving in the east direction, so this is east direction, this is west. At first, I'm really far away in the left direction. Then I get halfway through, I reach point B. I keep getting closer to it, and then I keep getting further away from it. So I get here, and then further, further, and then keep getting further away. And you can see that the slope of the line doesn't really change, but its location changes now. And finally, what if I started at point C? Right here. So the time doesn't change. I'm still using half the time here. In this case, initially, I'm very far away to the left, and then I start moving towards the point here. So if I were to draw it initially, I'm really far away. I move closer and closer and closer to the point, and you can see the slope of the line again is pretty consistent. And the lines are all straight, indicating that this is a constant velocity. You can see that the spacing between the dots are not changing. What if we were moving to the west? If the initial position was A here, or the reference point was A, if we were moving to the west, initially we were really far away from it, and we would get closer and closer. So that would be indicated very far away, and at the very end, we were right at reference point, so that would look like this. If the reference was right in the middle, that would mean initially, if you're moving west, initially we're here, so we are in the east direction. or positive direction. Right at the middle point, we are going to be right at the center or the reference, and at the end, we are to the left of our reference point, meaning that we are in that direction, and this will look more like this. And finally, if our reference point is a C, and if we're moving in the west direction, initially we're at 0, and then we get further and further away in the negative direction. We're not traveling as much in time, so I'm going to draw that somewhere here. So you can notice that in terms of the slope, in terms of value of the slope, if you were to actually compare them, the slopes are the same in terms of magnitude. The steepnesses are the same, they're just in opposite direction. So if you're moving in the direction of that you took positive, in this case we took positive to be in the east direction. If you're moving in the same direction, your slopes are going to be positive, and if you're moving in the negative direction, your slopes are going to be negative. Okay, let's keep moving on and on and on. Here we have a different situation. Let's imagine that we're moving in the east direction. So east is positive this way. And I'm going to start off with A being the reference point, so right here, and we're moving in this direction for the first set of graphs. So initially I'm right at the reference point, and then I start traveling in this direction, and you can see that the distances are getting much, 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 much larger as I'm moving in this direction. So initially I don't move too much, but then I start getting uh, longer and longer distances. So I'm not sure if I use the same number of dots here, but the idea is that initially I don't move much, but then I start to move more and more. And you can see that I get a nice curve here. So initially not moving much, but then the distance just keeps increasing a lot more, and you get this nice curve. If the position is B, things are slightly different. Um, we're going to have our reference point here. So initially we're really, really far away and in the left direction, and then we get closer and closer to B, and then we end up moving a little bit from C. So the line stays the same. It's just that it all happens at a different direction. So kind of looks like this instead. For the sake of this video, and we don't really need that many practices, so let's actually skip these two. And for homework, I'm going to assign you this question and this one. We can skip this one in the middle. And yeah, so try those ones for homework. These are the ones in which you're going in the left direction, and east is positive. We have a little bit more of this. Let's try. We don't need that many practice questions, so I'm just gonna skip these two and kind of focus on the first one over here, and you can do the second one as homework. But for the very first one over here, you can see if we were to take A as a reference, initially we're at the reference. And as we move, our distance, these arrows get bigger and bigger up to this point. So they get 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we kind of get a nice curve up to that point. Between these points, the spacing just keeps increasing about the same. So we go this much, we go this much, this much, this much. So these arrows that I just drew are going to go this way, but they're going to be consistent. So it's going to go up, up, up. And how many did I have? 1, 2, 3, 4. So 1, 2, 3, and 4. And after that, we can see after this point, the arrows still are big, but they're getting smaller. Like the difference between them are getting smaller. So you can see in the beginning, the differences between these arrows are getting more and more. The differences between these ones are consistent. And the difference between these ones are getting shorter and shorter. So if I were to draw them out vertically, it will kind of taper off like this. And if I were to draw this, kind of go like this, it would be pretty straight for this point, and it will taper off this way. So you can see initially the object is kind of starting to speed up, and then it kind of, in this region, kind of moves at a constant speed, and then it slows down towards the end. So having said that, you can try this one on your own and see it, and I will try to post the solution to that homework one later. Okay, we talked about motion diagrams and how we can transfer them into position time graphs, but let's talk about scalar and vector quantities. So scalar quantities is a quantity that has magnitude, size, and units. So an example of that would be 4.2 kilograms. We could mention 3.0 meters or kilometers. It doesn't really matter. All it has, it's a magnitude or size, and it has a unit. Whereas a vector quantity has a magnitude or size, it has a unit, and it has a direction. So for example, we can say 20.0 meters in the west direction. This is our size or magnitude. This is our unit, and this is our direction. Direction, there's different ways of representing direction. Sometimes square brackets are used. Sometimes you can just mention what the direction is. But in order to show it, we have to use what's called a vector quantity. And for position, we use a D with an arrow on top. So if I were to use distance or just some like a scalar quantity, the vector sign on top wouldn't be there, and this would just mean 20 meters. So if I give you this set of information, you know that an object is 20 meters away from something else. But if I give you this set of information, you know that compared to a reference point, an object is 20 meters away in the west direction compared to that reference point. And in real life, I can use reference point as like a tree. I can say that Sophia is 20 meters west of a particular tree. But if I told you that Sophia is 20 meters away from the tree, you don't know if it's west, if it's east, if it is north, or if it is south. So those ideas are not given to you if I just told you the scalar value, but if I give you the vector, you also know which direction the object is at. So here's the list of scalar quantities or vector quantities that we will be using a lot in our course. So scalar quantities, one of them is, the idea is distance, that is the length of a path traveled by an object, and its equivalent vector quantity is position, and this is the distance and direction of an object from a reference point. Total distance is the total distance traveled by an object in motion, and the path here does matter. So if you go back and forth and back and forth and back and forth and back and forth, we add up all those distances. Whereas for displacement is the change in position. So for example, if you were right here and if you moved in here and came back, the change in your position is 0. You haven't actually changed. You moved, but you haven't changed your position. So that displacement will equal to 0. To calculate, to show displacement or change in position, position is shown by a D with a vector above, and the change in position or displacement, the change is a delta sign, and position is this, so this represents change in position or displacement. It can also be calculated by subtracting the final position by the initial position. Change in time is delta t. The change is delta, represented by delta, and t stands for time, lowercase t. And the time, this is the time interval that we considered. And the total displacement is the sum of the magnitude of all the displacements. So if we have multiple displacement, we just add them like this. And we'll do an example soon to kind of get an idea of that. And algebraic representation of vectors, we can use different methods. So we use a variable, symbol, size, unit, and direction. So this is vector AB. So that if you have one position A and one position B, we show vector AB in this direction. Let's say this is 15 meters, meaning the size of this is 15, and it's in the east direction. BA, we can kind of switch the B and A. So if this is A and this is B, B to A, we can say it as negative 15 meters east. So if we switch the letters, that it becomes negative. Vector BA, if we're looking at the positive direction, it means it comes from B, it moves towards A. That's 15 meters, and we can see it's in the west direction. This is kind of like the scale diagram representation of it. And vector directions can be changed algebraically by a negative magnitude. For example, 15 meters east is equivalent to negative 15 meters west. And this can only happen with collinear directions, meaning directions that are in the same line. And if you look at our vector unit in 1 dimensions, all of these are already covered. Let's do a few questions. Let's do an example here. So we got Mr. Shateri, who starts at home and moves 700 meters east to the store. He then walks 200 meters west to the school. So let's sketch the situation. So we got Mr. Shateri starting at home. I'm actually going to just draw a line. I'm not going to use my artistic abilities in this situation. We're just going to label this as home. So Mr. Shateri first goes 700 meters east. So I'm going to take this side to be east. And Mr. Shateri goes here. He goes to the store. So I'm going to call that store. And then he walks left and goes in this direction, 200 meters west to the school. And this is 700 meters in that direction, and then Mr. Shateri turns back and travels 200 meters in this direction, and that's kind of like the sketch of the situation. And I can also label things. This is the first location, this is the first event. Being at home, moving to the store is the second event, and being at school is the third event. Now, taking the store as the reference, state the position of his home, the store, and school. We can do that. I'm going to take this position to be my reference point and state the position of his home. So from here, his home is 700 meters away, but since everything to the right is positive and everything to the left is negative, I have to say that the position of the home relative to the store is a negative 700 because it's in the negative directions. So the position of home in this case is equal to negative 700 meters. How far is the school? Well, that is going to be the third one, as labeled above, you can see the school is here, and the school reference to the store is 200 meters in the negative direction. Everything to the right, based on this reference point, is positive. Everything is in this direction is negative. So I'm going to say this is negative 200 meters, and I always need a direction. And since I'm taking everything to be right to be positive, I am going to say east for both cases. And the position of the store itself, that's position 2. And position 2, relative to the reference points, the store is right at the reference point. So that's going to be 0 meters away. So that's 0 meters in the east direction. Okay, now I have these. Now calculate the displacement from home to the store and the displacement from store to the school. I can do that. I'm going to move everything up, and actually I'm going to use the data that I'll use this so I can reference back to it. So the displacement from home in this case is number 1, to the store is number 2, is going to equal to, based on the equations that we saw, that's going to be position 2 minus position 1. So it's always the second one minus the first one. Position 2 is, I'm going to take east to be positive, and position 2 is 0, and position 1 is negative 700. Since 0 meters east that's just no direction, and I'm going to subtract that by the first one here, negative 700. If you're having trouble with following this, just make sure that you look at the vector video, and that should clear things up. We got 700 here, meters, and my sign convention is positive in the east direction, and that would mean the displacement from 1, which is home, to 2, which is the store, is equal to 700 meters in the east direction, and that makes sense. My vector shows that as well. And now displacement from store to the school. Store is 2, school is 3. So that's going to equal to the second one minus the first one. And I'm going to take positive east. And my third position, based on this value, is negative 200. So it doesn't matter which reference point you're choosing. In this case, I'm just being consistent and using store as the reference. And I'm going to subtract that by the second one. Second one is 0, and that's going to be negative 200 meters in the east direction. Let's make sure that makes sense. From store to school, I'm moving west. East is positive, so if I'm moving 200 west, that's equivalent to 200 meters east. So this can also be written as 200 meters west. Both of them are correct. Now finally, I'm asked to calculate the total displacement. So the total displacement is how far they went from the very initial position to the very final position. Initial position, we can see right away that that's 500 from our graph, but let's make sure we can do it algebraically, because when it comes to more challenging situations, sometimes you don't have a diagram and it will become challenging to do it using a diagram. So we know our answer is 500 meters east. I'm just going to scroll up and use 2 different methods to do this. One method is to find displacement from 1 to 3, which is the total displacement. So I'll write that down here. So the total displacement is the change in position from 1 being the initial event and 3 being the very end event of Mr. Shatteri's adventure. And this can be calculated by taking the third position and subtracting it by the first one. It's always last minus initial. So the third position here is negative 200. I'm going to take right to be positive, east. And sorry, third position here is negative 200 in the east direction. So that's going to be negative 200 minus the first position here, which is negative 700 in the east direction. So that's negative 700. When I do this, I get negative 200, negative and negative make it positive, and this becomes 500 meters, and my direction is east. So this is one way of doing it, and if you have the initial and final position, then use this method. This is going to be the most efficient method of finding it. Alternatively, you can find the total displacement by adding all the displacements. So we are going from 1 to 3, so we have to find the displacement from 1 to 2, and then we stop at 2, and we start at 2 again and go to 3. So we can use this idea. So displacement from 1 to 3 is 1 to 2 plus 2 to 3. Well, this is nice because I can use this method. I already have the displacement from 1 to 2. That's 700 in the positive east direction. So that's 700 plus I have the displacement in the from 2 to 3 as well. And this is saying negative 200 meters east. And we know that if east is this direction, if I'm adding that, I have to do negative 200. You can also, if you had 200 meters west, because west is opposite to east, you would have to use the negative. Either way, it's the exact same value that goes here. And 700 plus negative 200 is 500 meters, and that's in my positive direction here, which is east, and you can see both methods yield the exact same answer. You would use this idea if you only had the positions and you didn't have the displacements, then this would be a very good method. If you only had the displacement and you didn't have any positions, if you were not asked to calculate these ones, and if you were only asked to calculate this one, then use this method. This one would be easier. If you have the displacement, this one is easier if you have the positions. Finally, we're asked to find the total distance traveled, and distances don't have any direction, so I'm going to move things up a little bit. And the total distance will be the distance traveled from the very beginning to the very end, and that's going to be the distance traveled from location 1 to 2 plus the distance traveled from location 2 to 3. Well, now I no longer need directions. Note that I don't have arrows for distance, and I don't have any negative values. So distance from 1 to 2 was 700 meters. I don't care about the direction, and I don't care about any negative signs in this case. So I'm just going to put 700 meters was what Mr. Shateri traveled first, and then Mr. Shateri traveled another 200 meters. I don't care about direction. I don't care about the negative sign. I'm only looking at the magnitude or the size of the amount that was traveled. So that's 200, making this 900 meters. And I don't need to include direction. So the total distance traveled by Mr. Shateri is 900 meters. And that makes sense. He traveled 700, then he traveled 200. And this is the answer there. So I also like to highlight my answers, so or just box them. So in this case, I'm just going to use a different color and highlight all my answers so they're nice and clear. Okay, the final question here for today's lesson says outline whether magnitude of the total displacement is larger or the total distance. So we can see in terms of magnitude, actually, if I scroll down, no, I don't need to scroll down. The displacement, the magnitude of it was 500. When we're talking about magnitude or size, we don't care about direction or negative signs. 500, whereas the total distance was 900 meters. Well, the displacement will always either be equal or smaller than the distance. And the reason for that is when you're looking at change in position, you may go and come back, and if you come back, your displacement in terms of magnitude reduces in size. Whereas if you go straight, when you're doing your distance, you do care that you're going in this direction and then you're going in this direction, and you're just adding all of those up. So if you were to change direction, so here, if moving in same direction, then I'll just write size. Size is same if changing directions, then size is smaller for position. And that's the video for today.